Hi, everybody. Welcome back to Differential Equations. Today we're going to put the finishing touches on Euler equations. There's still a couple of things we need to address. When things go wrong, part 3. And I guess this may be the last of the things that can go wrong. We may have a situation where the right side of an Euler equation contains a term that also happens to be an independent solution of the complementary equation. Now, if this were a linear differential equation with constant coefficients, we'd just take that term on the right side and multiply it by x, and that would be our proposed solution. But we're not dealing with linear differential equations with constant coefficients, but we're dealing with an Euler equation. So if we're doing method of undetermined coefficients, and the right-hand side of the Euler equation is a polynomial that contains a term that is essentially the independent solution of the complementary equation, what do? Instead of multiplying it by x, since this is an Euler equation, what do you think we do? If you guessed multiply by natural log of x, you're right. That turns out to be the thing to do. So let's look at an example where we have to do exactly this. Okay, first thing we have to do is find the solution to the complementary equation. This is an Euler equation, so we guess the solutions of the complementary equation are of the form x to the lambda, or y equals x to the lambda. So y equals x to the lambda. Y prime is lambda x to the lambda minus 1. And y double prime is lambda times lambda minus 1, x to the lambda minus 2. And we can simplify that a little bit. We're going to take these things and plug them into the complementary equation and solve for lambda. So let's see, we have x squared y double prime, and y double prime is lambda squared minus lambda x to the lambda minus 2. Then we have minus 2x y prime, which is lambda x to the lambda minus 1. And then we have 2y. Whoops. And y is x to the lambda. And all of that equals 0. So what do we have? X squared times x to the lambda minus 2 is just x to the lambda. And here x times x to the lambda minus 1 is x to the lambda. Each term has a factor of x to the lambda, so we divide both sides by x to the lambda. So how does this work? Lambda minus 1, lambda minus 2, I think that's it. Negative lambda, negative 2 lambda is negative 3 lambda, that's it. So lambda sub 1 equals 1, lambda sub 2 equals 2. C1 x to the lambda 1 plus C2 x to the lambda 2 x to the first, x to the second. So that's our complementary solution, I hope. What was our original equation? X squared y double prime minus 2xy prime plus 2y equals 5x squared. We're going to assume that our particular solution is a polynomial that has exactly those powers of x that are found on the right side of the equation. So we're guessing that this is what our particular solution looks like. And if we're not careful, we may proceed from here without seeing the booby trap. This term is one of the independent solutions of the complementary equation. So if we plug this into our equation, we're not going to get 5x squared. If we plug this into our equation, we're going to get 0, because this is one of the solutions of the complementary equation. So here's how we fix it. We take what we had proposed to be our particular solution, and we multiply it by natural log of x. So this is now our proposed particular solution. The thing to do now is compute y prime and y double prime and plug them into this equation and solve for a. So y particular is a natural log of x, x squared. Y prime particular, we compute the derivative of this, but oops, this is a product. So we're going to have a, and then we're going to have first times derivative of the second plus second times derivative of the first a times 2x natural log of x and a times x. Now I guess we have to do y double prime particular. So I have 2a times the product x natural log of x. So we have first times derivative of the second plus second times derivative of the first. And then we compute the derivative of this guy. We just get a. X times 1 over x is just 1, so we have 2a times 1 is 2a, and 2a times natural log of x and we have a here. Well, a plus 2a, let's just make that 3a. And those should be our derivatives. And we want to plug those into the original equation, which was, oh, I don't know what it was. X squared y double prime minus 2x y prime plus 2y equals 5x squared. X squared y double prime, 2xy prime, 2y, 5x squared. Okay, good, good, good. X squared times y double prime minus 2x times y prime, so that's 2ax, natural log of x, plus ax, plus 2y, and y is a natural log of x, x squared, and all of that is supposed to equal 5x squared. So let's count all our marbles and see what we get. As far as ax squared goes, no, let's say ax cubed. You know, I think I have a problem here somewhere. No, I'm okay. I'm okay. I have 3ax squared here. So 3ax squared. And I have minus 2x ax, or minus 2ax squared. And that may be all. I don't see any other ax squared terms. Now, a natural log of x, or what about a x squared natural log of x? Here we have 2ax squared natural log of x. And here we have minus 4 ax squared natural log of x. And over here I have plus 2ax squared natural log of x. And I think that accounts for all of my terms. And thankfully that turns out to be 0. This turns out to be 1. And all of this is equal to 5x squared. So that is ax squared equals 5x squared. So a equals 1, I hope. Let me go back and see what my notes say. My notes say I'm an idiot. Ax squared equals 5x squared. Yeah, let's see. A and 5, they must be the same. Okay. Well, we'll just pretend we didn't see that. So there's our particular solution. And heavens to Betsy, what was our complementary solution? C1x plus C2x squared. with linear differential equations with constant coefficients, there are only certain equations that we can use undetermined coefficients on. And those equations have as their right side any combination of polynomials, sines, cosines, and exponentials. If we have something other than those on the right side, we can't use undetermined coefficients. Euler equations have stronger restrictions. It turns out method of undetermined coefficients on Euler equations only works if the right-hand side is a polynomial. So if we have sines, cosines, and exponentials on the right side of an Euler equation, undetermined coefficients won't work there. We have to use variation of parameters. So if we have something other than a polynomial, oops, don't do that. The right-hand side is not a polynomial. So it looks like we have to use variation of parameters. So find the solution of the related complementary equation. And we assume that our solutions are of the form x to the power of lambda. So y equals x to the lambda. Y prime is lambda x to the lambda minus 1. Y double prime is lambda times lambda minus 1 x to the lambda minus 2. And we tidy that up a little bit. So let's see. X squared y double prime. X squared y double prime is lambda squared minus lambda x to the lambda minus 2. Three x y prime and that's lambda. No, it's not. Y prime is lambda x to the lambda minus 1. And then we have y. And x squared times lambda to the x squared times x to the lambda minus 2 is x to the lambda. X times x to the lambda minus 1 is x to the lambda. Each term has a factor of x to the lambda, so we divide all three sides by x to the lambda. And that looks like lambda plus 1 quantity squared. And in fact, that's what it is. So we have the dreaded double root. So when we have a double root, we multiply the second term by natural log of x to get our independent solution. So that is our complementary solution. To get our general solution, we essentially vary the parameters C1 and C2 and make functions out of them. So this C1 becomes A of x. And this C sub 2 becomes B of x. This is what our general solution looks like for some unknown functions, A and B, that constitute a pair that will make this a solution to the original equation. So now that we've parameterized C1 and C2, I guess we don't need this anymore. Okay, compute the first derivative. And we have a product here. So we use the product rule. First times derivative of the second plus second times derivative of the first then we move on to this term, and it's the product of three factors. So I'll tell you how I'm going to apply the product rule to this. Derivative of the first times the other two, plus derivative of the second times the other two, plus derivative of the third times the other two. So derivative of the first times the other two plus derivative of the second times the other two. And tell you what, this is ugly. Derivative of the second, let me say that that's x to the negative 1 instead of 1 over x. Derivative of the second times the other two plus derivative of the third times the other two. Okay, that looks good. Let me simplify this a bit. And let me correct a mistake here. Derivative of x to the negative 1 is negative x to the negative 2 okay? And I'll say a prime of x, x to the negative 1 here, plus b prime of x, natural log of x, x to the negative 1 there. And x negative 1 is x to the negative 2. Minus b of x, natural log of x, x to the negative 2. And I'm going to impose my second restriction. My first restriction was that this pair of functions, a of x and b of x, actually do make this expression the solution of our Euler equation. The second restriction I'm going to impose is that the sum of these two things is going to equal 0. Whoops. Oh, that's right. I have yet to compute y double prime. So, we got a product here, so we'll have first times derivative of the second plus the second times the derivative of the first So first times derivative of the second minus or plus a minus the second times derivative of the first. Okay. We got a product here. First times derivative of the second plus the second times derivative of the first and now this last one. I'm just going to take this minus sign and distribute it over the three terms that give us this derivative. Derivative of the product of three functions, I'm going to do derivative of the first times the other two, derivative of the second times the other two, derivative of the third times the other two. So b prime times the other two plus derivative of the second, x to the negative 1, times the other two, derivative of the second times the other two, b of x, times x to the negative 2, and then derivative of the third times the other two, b of x natural log of x, and let's simplify this. This will be 2ax, x to the negative 3, minus a prime of x, x to the negative 2, and I'm going to move this term over here for very selfish reasons. B prime of x, x to the negative 2. No, I'm not either. No, I am not either. I'll stick with the selfishness, but it's actually this term I want to move over here. There's a negative sign out front, so negative b prime of x, natural log of x, x to the negative 2. I took this term and moved it over here because I'm a very selfish person. And I have some horrible motives here. So we have negative 2bx x to the negative 3 plus b prime of x, x to the negative 2, and I'm going to have to keep track of this. Okay. X to the negative 2 b prime of x. This term I've already accounted for. This term went right there. I have x to the negative 1, x to the negative 2 is x to the negative 3 times bx. but there's a minus sign out front. And I have this term, negative garbage, but there's a minus sign out front, so it should be plus 2 bx natural log of x times x to the negative 3. That should be negative 3 right there. Now, let me just look this over and make sure I haven't done anything horribly wrong. 2ax x to the negative 3, negative x to the negative 2a prime of x, and negative b prime natural log of x, x to the negative 2, negative 2 bx x to the negative 3, b prime x, x to the negative 2, x to the negative 1 times x to the negative 2 is x to the negative 3, times negative b of x, and then I have negative a negative 2x to the negative 3, b of x natural log of x. Yipes, that might actually be error-free. Now, I'll tell you why I put these two terms next to each other. These two terms look a lot like these two terms, except the signs out front are changed. And instead of x to the negative 1, we have x to the negative 2. Well, I can fix that. I'll factor out x to the negative 1. No, I'll factor out negative x to the negative 1 from each term. And that will give me a prime of x, x to the negative 1, plus b prime of x, natural log of x, x to the negative 1. And what we have in the parentheses here is this, which we said equals 0 when we imposed that second restriction. So this whole piece of junk is 0. And I'm running out of blackboard space, so I think now would be a good time for me to summarize what I've done so far. I'll move this up here. Y prime is negative ax, x to the negative 2, plus bx, x to the negative 2. You know what? I didn't do anything wrong, but I see a similarity between these two terms and these two terms. So I'm going to put this one up here. And I'll put this term over here. Yeah, I just moved this term over here. And let me make sure I've copied correctly. I think I have. And now let me write down y double prime. Two ax x to the negative 3 these two things equal 0. And I didn't notice this before, but those two things are like terms, aren't they? Bx to the negative 3, bx to the negative 3. We can put them together, minus 3bx, this term and this term, minus 3bx, x to the negative 3. And I'm going to stick this term right under that one. And this term right here, 2bx natural log of x, x to the negative 3, looks an awful lot like this term. So I'm going to take this term and stick it right here. So plus 2bx natural log of x, 2bx natural log of x, x to the negative 3. So it looks like the only thing I haven't accounted for is this guy. Okay. Now let me make sure that that's the way I want things. I think it is. I think it is. Well, if I have anything wrong, it's too late now. We're going to plug these into the original equation. So here's my x squared y double prime. That's going to be equal to x squared times this thing. So essentially I take each term and raise the power of x by 2. I'm taking everything and multiplying it by x squared, so add 2 to each exponent. So I should have 2ax, x to the negative 1, plus 2bx, natural log of x, x to the negative 1, minus 3bx, x to the negative 1, plus b prime of x, x to the 0. Okay. And let me make sure this is what I want. I think it is. Next, we add 3x times y prime. So we're going to take every term here and multiply it by 3. And we're going to multiply it by x. So we raise the power of x by 1 in each term, and we multiply each term by 3. So we'll have negative 3ax, x to the negative 1, minus 3bx, natural log of x, x to the negative 1, plus 3bx, x to the negative 1. I think that's what I want. And then I add y. So I have ax to the negative times x to the negative 1, bx, natural log of x to the negative 1, oh, is that it? I guess it is. And we add them all together. And this plus this is 3ax, x to the negative 1, minus 3ax, x to the negative 1. These three things add up to 0. Likewise, these three things add up to 0. These two things add up to 0. All I have left is b prime of x. Now over here I have x squared y double prime plus 3x, y prime plus y, and that's equal to b prime of x. But according to our original equation, that's also equal to x natural log of x. Okay. So I think I can solve for b of x. I think I can do that. It's not my favorite thing to integrate, but I guess I can do it. I'm going to turn this around because I have a sneaky suspicion that I have to use integration by parts. So that will be my U and this will be my dV. And if I'm right, I should get uv minus the integral of v du. Okay. U equals natural log of x. Du is, let's say, x to the negative 1 dx. dv is x dx. And if we integrate, we get v equals 1/2 x squared. Okay. So I get uv, which is natural log of x times 1/2 x squared. So there's my uv minus the integral of v du. Okay, integral of x squared is integral of x is 1/2 x squared times negative 1/2. So there's b. b of x is 1/2 x squared natural log of x minus 1/4 x squared c1. I hope. Oh, I really hope that's what it is. Now, how do we get a of x? When we plugged all of this junk into the original differential equation, we were left with b prime of x equals x natural log of x. I don't see us getting anything that will give us a prime of x other than the fact that our second restriction and thank goodness I wrote it down here, or at least I think I wrote it down here. Did I write it down here? No, I didn't. Ah, my goodness. Yeah, I did. A prime of x, x to the negative 1, plus b prime of x, natural log of x, x to the negative 1, is 0. Let me make sure I wrote that down right. Okay. We can use this restriction to find A prime because we know what B prime is. B prime is x natural log of x. And we're going to take x natural log of x and plug it in this equation for B prime. By the way, there should be a plus sign here. I just noticed it. And I want to correct it before I forget that that's not what it should be. Okay. A prime of x, x to the negative 1. X times x to the negative 1 is 0. This is natural log of x squared. Multiply both sides by x. Oh, so all we have to do is integrate this thing to get A. Well, nobody ever said life was fair. X natural log of x squared. I smell integration by parts again. Okay. I'll switch these two around. And this nice fella right here is going to be U, and that's going to be dV. And we'll remember that we have a minus sign out front. So uv minus the integral of v du so let's see. U is natural log of x squared du is 2 natural log of x to the first times derivative of natural log of x, which is x to the negative 1, dx. So du is 2 natural log of x, x to the negative 1 dx. And what about v? V is x dx. No, I'm sorry. dv is x dx. If we integrate both sides, we get v equals 1/2 x plus c2. Okay. So I have negative quantity uv, so that's natural log of x quantity squared. And v is 1/2 x plus c2. And then I have minus the integral of v. Oh, never mind the c2 yet. I will put that in after I finish integrating. Yeah, why make life more difficult when I don't have to? uv 1/2 x squared. V is 1/2 x squared. So uv minus the integral of v du. So that's 1/2 x squared. And du is 2 natural log of x, x to the negative 1 dx. So 2 natural log of x, x to the negative 1 dx. And that's negative 1/2 x squared. I'll put this out front. Natural log of x quantity squared minus the integral. Let's see, 2 and 1/2 cancel. X squared times x to the negative 1 is just x. Natural log of x dx. And it looks like integration by parts again. But you know what? Somewhere I integrated x natural log of x in order to compute b. As a matter of fact, b prime was x natural log of x. And so b of x, this thing, is the integral of x natural log of x dx. Oh, thank goodness, I'm not going to have to think too much more. This integral is equal to this thing. So I have minus quantity, 1/2 x squared natural log of x okay, minus 1/4 x squared plus C2. And let me make darn sure that's what I want to get. Oh, you know, I think it is. Son of a gun. Okay. So I can erase all of this junk. This piece of junk down here, once I simplify it, will be a of x. So I'll write that down here. And I have a negative sign to distribute to everything inside. So let's see, negative 1/2 x squared natural log of x squared. And I have minus times minus is plus. So I'll keep the sign of everything in here the same. 1/2 x squared natural log of x minus 1/4 x squared plus C2. And let me make sure that's really what I want to get. I'm not quite sure about that sign, whether it should be plus or minus. I'll keep it the way it is for right now. Well, let's see what we get. Our solution is y particular equals a of x times x to the negative 1 plus b of x natural log of x, x to the negative 1. A of x, negative 1/2 x squared natural log of x quantity squared plus 1/2 x squared natural log of x minus question mark 1/4 x squared plus c2. So there's A of x. And I need to have x to the negative 1. And then plus b of x. Ooh, what's b of x? This piece of junk up here. One half x squared natural log of x minus 1/4 x squared plus c1 times natural log of x, x to the negative 1. Okay, distribute, distribute, distribute. Let's see, x to the negative 1 times x squared will just be x. X to the negative 1 times x squared will just be x. Minus, that may be a plus. X to the negative 1 times 1/4 x squared is x plus c2x to the negative 1. Natural log of x times x to the negative 1 times this mess, let's say 1/2 x to the negative 1 times x squared is just x. Natural log of x times natural log of x, natural log of x squared. Oh, goody, goody, goody. Let's see. Minus 1/4 x to the negative 1 times x squared is just x times natural log of x plus C1 natural log of x, x to the negative 1. And what happens? I have negative 1/2 x natural log of x squared, and I have plus 1/2 x natural log of x squared. So those two things wipe each other out, thank goodness. And 1/2 x, 1/2 x natural log of x minus 1/4 x natural log of x. So let's see. These are like terms, just different coefficients. 1/2 minus 1/4. So that's going to be 1/4 x natural log of x. So that takes care of this. And it takes care of this. And I have negative 1/4 x question mark. And then the other two terms are exactly what they should be because they are our complementary solution. And what am I thinking? I did say general solution, didn't I? So this is not particular. This is general. And let's put a note of finality to this. Solution via variation of parameters. This is definitely the complementary solution. And I'm fairly confident that this is our particular solution. So if we don't have a polynomial on the right side of our Euler equation, we have to use variation of parameters. Hopefully some of the ones that we have for homework will be a little bit easier. Speaking of homework, they've been assigned previously If we haven't done them, let's do them. Five, 15, 20. These specifically are Euler equation exercises. Work on those. I do have some good news. This is going to be the end of the new material for the course. Nothing new for the rest of the course other than to prepare for test 3 and the final exam. And it's been a pleasure teaching you. And again, remember what we said yesterday about Isaac Newton. His greatest work was done in the years that he was in seclusion on his farm away from the university. He was there because the bubonic plague was ravaging London. And so he left the university until the plague subsided. And the vast majority of his mathematical and scientific achievements were accomplished there. Don't worry about what we can't do. Just do what we can do and do it well. This isn't going to last forever. But in the meantime, let's make sure that we act prudently and that we act productively as well. So off to the salt mines, work on this stuff, and I'll give you some things to look at in preparation for test 3 and the final exam.